This is our lecture video for Chapter 16 as part of our series on aqueous ionic equilibria. In this video, we will be looking at the titration curves of a weak acid with sodium hydroxide. We will be also looking at titration curves of polyprotic acids, as well as how indicators work. Now, to begin with, I'd like to show you this representative titration curve of a weak acid with sodium hydroxide. And I wanted to highlight some of the differences that we saw with the strong acid, strong base, with the weak acid, strong base. So notice that if we look at the inflection point here, this inflection point is around 8, so a pH of 8. So at the equivalence point, the pH is actually higher than what we consider a neutral pH. So this is because at the equivalence point, all of the sodium hydroxide has consumed all of the weak acid, and the only thing that's left is the conjugate base that's formed from neutralizing the weak acid. So the weak base is what's causing the pH to be basic at the equivalence point. Now, something else that's different about the weak acid, strong base titration curve compared to the strong acid, strong base is that we have a buffer region. So the buffer region is where we're going to have a type 2 calculation. This is any point after some sodium hydroxide has been added, but before you reach that equivalence point. So at the equivalence point, we've added 25 mils of sodium hydroxide, and at 12.5 mils we should have what's called the half equivalence point. So the half equivalence point. And the half equivalence point is the middle of the buffer region. So the buffer region is anywhere after some sodium hydroxide has been added but before the equivalence point. Now, if we compare this to the strong acid, strong base, remember it doesn't have a buffer region, but also that titration curve didn't have this little increase here, this little hump here. If we were to draw a tangent line through this part of the graph, so where it goes through this half equivalence point, where the tangent line intersects with a line, this is where we have the effective region. So this is the effective buffer region. And in this titration curve, we're actually looking at acetic acid. And the pKa of acetic acid is 3.7. So that's where we notice that at the half equivalence point, the pH, so if we draw the line right here, the pH equals the pKa only at the half equivalence point. And so in this buffer system, it would be effective from about 4.7 to 2.7. So notice that that's where we get this idea of the effective buffer region, because you have very little change in the pH when added, when base is added. Now let me prove to you that the pH equals a pKa at the half equivalence point. If you'll remember the Henderson-Hasselbalch equation, where the pH equals the pKa plus the log of the base over the acid. So that base over the acid, so it would be the A minus over the HA. At the half equivalence point, you've added enough base to neutralize half of the acid. And if half of the acid has been neutralized, the other half is the conjugate in the conjugate base form. So at the half equivalence point, the concentration of the conjugate base will equal the concentration of the weak acid. So if those two are the same, and I plug this into my Henderson-Hasselbalch equation, notice that the log of 1 is 0. So only at the half equivalence point does the pH equal the pKa. So in your lab, you will be creating titration curves very similar to this. And remember, there are 4 types of calculations that will be done. There is the initial calculation, And this calculation will be done only once when you are looking at the pH of the weak acid when no sodium hydroxide has been added. Then you will be adding several volumes of sodium hydroxide and calculating the pH at each of those points. And in this region, you'll be doing all of type 2 calculations. You will be in the buffer region. Then at type 3, this calculation is only done once. This is a calculation of the pH at the equivalence point. And then after the equivalence point, you will be calculating the pH when you have excess sodium hydroxide. So this is where Excel will be your friend. If you do one of these calculations once in Excel, you can copy and paste down and do all the rest of the calculations very easily, rather than doing all these calculations by hand. So let's look at some of the calculations that we'll be doing. So we're looking at a weak acid with a strong base, and we've got 25 mils of 0.1 molar formic acid in a bottle, so in our reaction flask, and we're going to be adding 0.1 molar sodium hydroxide. So remember, our first type of calculation is when no base is added. So if no base is added, the only thing that we have in there is the formic acid. And if we write our chemical equation for the formic acid, when dissolved in water, remember it establishes an equilibrium, so this is a two-way reaction. So the formic acid in water will produce the formate ion and the hydronium ion. Now we're going to calculate the initial pH. I set up my ice table, so I initially have 0.1 molar formic acid and none of the formate ion. I set up my change. I'm going to lose some of my formic acid and produce some of the formate, and I have my equilibrium values. I look up in a table to find my Ka of formic acid. In the table I find that my Ka is 1.8 times 10 to the minus fourth. Well, if the Ka is the products over the reactants in my mass action equation, I substitute in the values that I found at equilibrium. So I get x squared over 0.1 minus x equals 1.8 times 10 to the minus fourth. And I'm going to use the approximation that x is small enough. And so when I solve for my x squared, I take 1.8 times 10 to the minus fourth, multiply by 0.1, and then take the square root to get my hydronium concentration. And just to show you that this approximation is valid, we took our hydronium concentration, divided it by our initial concentration, multiplied by 100, and this is less than 5%. So we're okay to do the approximation. Now going back to my reaction where I've determined my hydronium ion concentration, I can take the negative log of that to find my pH, and my pH initially, before any sodium hydroxide is added, is 2.37. So that's the first type of calculation, and this calculation is only done once in a titration curve. Now the next type of calculation, we have some added sodium hydroxide added to the formic acid. So when sodium hydroxide is added to the formic acid, this is a neutralization reaction. And remember, neutralization reactions are one-way reactions, and we have to take care of the one-way reactions first. I'm going to calculate my initial moles of formic acid by taking my volume of formic acid, and remember this is the volume in my flask at the bottom of my burette, multiply it by my molarity to get the number of moles of formic acid inside my flask. And this is, remember, is before the equivalence point. Now we're going to add 5 mils of sodium hydroxide. I need to determine my moles of sodium hydroxide, and my molarity of my sodium hydroxide is 0.1. Multiply it by my 5 mils to get my moles of sodium hydroxide. So I'm setting up an ice table where I'm taking care of that neutralization reaction first, that one-way reaction first. So at the beginning I have 0.0025 moles of formic acid, and I have 0.0005 moles of the hydroxide. So during the neutralization reaction, because it's a 1-to-1 mole ratio, I'm going to consume all the hydroxide because this is my limiting reagent. So I'm going to take that amount of hydroxide from the formic acid, and when you neutralize the formic acid with the hydroxide, you will produce the formate ion. So remember that CHO2 minus, that's a formate ion. So after the neutralization reaction, I'll have 0.002 moles of formic acid left over and 0.0005 moles of the formate after the neutralization. Now that I've dealt with the neutralization reaction, now I can deal with the equilibrium, because remember the formic acid will establish an equilibrium in water as it becomes deprotonated. Now I can either choose to set up an ice table or use the Henderson-Hasselbalch equation, which simplifies things. But the only reason why we can use the Henderson-Hasselbalch equation in this situation is because we're in a buffer. So only at calculation type 2 with weak acids, strong bases, or type 2 with weak bases, strong acids, can you use the Henderson-Hasselbalch equation, because those are your buffer regions. So only in the buffer region can you use the Henderson-Hasselbalch equation. So if I use my Henderson-Hasselbalch equation, remember pH equals the pKa plus the log of the base form, the conjugate base over the acid. So we looked up the Ka value of the formic acid. It's 1.8 times 10 to the minus 4th. I take the negative log of that to get my pKa, and I get a value of 3.74. I then plug in the moles of formate ion over formic acid. And notice that I didn't put in molarities, because if I divided both of these by the total volumes would be the same. They'd cancel each other out, so I can leave this as moles. So when I do the calculation here, I get a pH of 3.14 after 5 mL of sodium hydroxide has been added to the formic acid solution. Our third type of calculation is at the equivalence point. So remember, we're still neutralizing the formic acid with the sodium hydroxide, and that's a one-way reaction. And at the equivalence point, because the molarities of the sodium hydroxide and the formic acid are the same, the volumes added will be the same. So at the equivalence point, we will have added 25 mL of sodium hydroxide. Now, if you are asked to find the equivalence point and you're given the molarity of one solution and a volume, and you're given the molarity of the other, but you're not given the volume, remember the moles are going to be the same. So you take the molarity times the volume to get the number of moles of formic acid, and the number of moles of formic acid have to equal the moles of sodium hydroxide, so that's a 1-to-1 mole ratio. So then you have the moles of the sodium hydroxide and the molarity, so you can find the volume of sodium hydroxide at the equivalence point. Okay, so I digressed a little bit, but at the equivalence point, we've added 25 mL of sodium hydroxide. So at the equivalence point, when 25 mL of sodium hydroxide is added, we have 2.5 moles, 2.5 times 10 to the minus 3rd moles of sodium hydroxide. And remember, this is the same amount of formic acid that was initially in the flask. So we have to take care of the neutralization reaction first. This is that one-way reaction. And remember, at the equivalence point, we have equal moles of the formic acid and the hydroxide. So we really don't have a limiting reagent. Both are kind of limiting our reaction. And after the neutralization reaction, we have no more formic acid. We have no more sodium hydroxide. All of it has been converted to the conjugate base. So we create 0.0025 moles of the formate ion. Now that I have taken care of my neutralization reaction, I can now deal with my equilibrium. Because remember, the conjugate base that's formed from the weak acid is still a weak base. So it will establish an equilibrium when in water. I write my equation for my formate ion dissolved in water. So this is my base. When it's dissolved in water, it will become protonated to form some of the conjugate acid, which is the formic acid, and the hydroxide ion. So now that I'm working with a base and we're working with a basic system, I write my mass action equation using my Kb and my products over my reactants. Now to find my Kb, remember I knew my Ka from earlier as 1.8 times 10 to the minus 4th, and I know the Kw is 1 times 10 to the minus 14th. I can find my Kb value, which is 5.6 times 10 to the minus 11th. Now I find my molarity of my formate ion. So this is my number of moles of formate. And I divide it by my total volume in my reaction. So remember, I started off with 25 mils of formic acid. I then added 25 mils of my sodium hydroxide at the equivalence point. So I now have a total of 50 mils in my reaction. So I've had 50 mils in my Erlenmeyer after I've added the 25 mils of sodium hydroxide from my burette. So my concentration of my formate at the equivalence point is 5 times 10 to the minus 2nd molar formate ion. I substitute in my initial concentration of my formate ion, and notice how this looks very similar to my type 1 calculation. In type 1 I was working with Ka and I only had the weak acid in solution, but at the equivalence point I only have the formate ion in solution, so I have to deal with the Kb. But my Kb equals the x squared over 0.05, because here I've done a simplification, and that x represents my hydroxide concentration. So if my hydroxide concentration is 1.7 times 10 to the minus 6 molar, I can take the negative log of that to give me my pOH, and then 14 minus the pOH gives me my pH. So at the equivalence point, my pH equals 8.23. Now again, at the equivalence point, there's only one equivalence point in a titration curve, so this calculation is only done once. Now after the equivalence point, the calculations become a little bit easier, because after the equivalence point, you have an excess of the strong base. So let's look at our fourth type of calculation, and this time we're going to be adding another 5 mils after the equivalence point, so our total volume of sodium hydroxide that has been added is 30 mils of sodium hydroxide. So using our volume of sodium hydroxide that's been added and our molarity, we determine the number of moles of sodium hydroxide. And remember, we have to take care of this one-way reaction first, which is the neutralization of the formic acid with the sodium hydroxide. So again, we start off with 2.5 millimoles of the formic acid and 3 millimoles of the hydroxide ion. When I subtract what's used during the neutralization, I'm going to consume 2.5 millimoles of the formic acid and 2.5 millimoles of the hydroxide ion. And remember, the formic acid gets converted into the formate ion, so that at this point we have 0.5 millimoles of the hydroxide ion left, and we have 2.5 millimoles of the formate ion. Now, because of the excess strong base, there's no equilibrium to deal with. The strong base is going to be so much more powerful than the formate ion that's in there. It's going to be the strong base that sets the pH of the solution. So I determine the amount of sodium hydroxide in excess. So remember, we have that 0.5 millimoles of sodium hydroxide in excess that's left over after the neutralization. I find my molarity of that excess sodium hydroxide by dividing those moles by the total volume. So it's 25 mils of HCl plus the 30 mils of sodium hydroxide give me a total volume of 55 mils. And the concentration of my sodium hydroxide is 0.0091 molar sodium hydroxide. And because this is a strong base, it completely dissociates. So the 0.0091 is the concentration of my hydroxide. I can take the negative log of that to find my pOH. And remember, I'm still trying to find the pH. So 14 minus the pOH gives the pH. So that gives me a pH value of 11.96 after 30 mils of sodium hydroxide has been added to the acid solution. So this is after the equivalence point, and this is a basic concentration. So this fourth type of calculation will be repeated several different times after the equivalence point. So this is why Excel is very useful to you. So you only have to do it once in Excel and copy and paste it down for the rest of the volumes of sodium hydroxide that have been added.